In this video, we're going to cover active reinforcement learning. This should extend what we studied in class, which included some high-level discussion of general types of reinforcement learning, as well as a more in-depth view of passive reinforcement learning. And we'll talk about that a little bit in this video too. So the outline is that we're going to talk about active reinforcement learning, motivated by looking at passive reinforcement learning first, and then we'll talk about why active makes more sense. And then we'll talk about active adaptive dynamic programming, or active ADP, and then Q-Learning, which is a new view of reinforcement learning than what we've seen so far. So let's review passive learning. So when we think about what we've looked at in class, we were examining the scenario where we, as the learning algorithm, get access to essentially recordings of an agent that's running some fixed policy, right? So we just sort of watch this agent try to get rewards in some environment just by running some policy. And then after it finishes the runs, after we receive all these recordings, we can go in and use the rewards that we saw, the state transitions that we saw, the actions that we know the policy was trying to execute, and then attempt to estimate the utility function. And that's sort of the goal. And so the first sort of thought experiment version of this was direct utility estimation, where you just essentially treat each time step, each action that we've taken in the recordings as an example of what the future rewards will be, and then we just directly estimate the utility using those samples. So that's direct utility estimation. Then we talked about adaptive dynamic programming, which is a fancy name for essentially estimation of the transition probabilities and then running policy iteration on top of that, right, using our estimated rewards and estimated transition probabilities. And finally, we talked about temporal difference learning. And this is a strategy that updates our current estimates of the utilities every single time we make a transition, every single time we observe a transition where we take an action and we end up in a new state, or maybe the same state, but we end up making a transition to another state. And the idea is we will compare the estimated utility of the state that we are in versus the state that we transition to, and we treat that essentially as a sample of what we think our current expected future reward is going to be, and we compare that to what our current estimate is. And if it's bigger than it should be, then we increase our estimate. If it's smaller than it should be, we decrease our estimate. So pretty straightforward. So all this is in the book, so you can have a look closer, or we can talk about it more in class. But let's think about now, what are the problems with passive reinforcement learning? And there's kind of a big problem. I realized it in class, and I sort of got tripped up on it on the board when we were talking about it, because it really is a major flaw in the passive reinforcement learning framework. And that's that we don't really have a good way of updating our policy even after we estimate the utilities. Even if we estimate the exact utilities from these schemes, we don't know the transition probabilities. Or rather, at least with direct utility estimation, we don't know the transition probabilities. But with ADP, we're estimating the transition probabilities, but we don't really have a very good estimate, because all we can sample are the transitions that happen when we take the actions according to our fixed policy, according to the fixed policy that the robot is running around, implementing, and that means that we have a very limited sample of what the transitions will be for any action that's not in that original policy. And so this gets sort of fixed a little bit if we run a passive ADP, update our agent that's operating in the environment with a new policy, and have that agent play again, and then we collect more data and then repeat. And that's, that sort of fixes it, but it doesn't really, because if you think about, so here's one thing. We are estimating U's, and we have a pretty good idea that we can get a good estimate of U. We can estimate these utilities pretty well from these passive recordings of an agent running around an environment. But the transition probabilities, again, we can only expect to get a good estimate of the transition probabilities for the actions in our policy. And what that means is that for any action that's not in our policy, what is our estimate of the transitions? We don't know. We don't have any idea. I mean, maybe in grid world, it kind of makes sense to assume that the policy, that the randomness is 0, and said that you, whenever you try to move right, you always move right. Maybe that's the idea, but we don't know that. I mean, we don't know. There's nothing really tying the notion of, move right, the action move right, to the transition to the state on the right. It really is just, it really is that there's some action. It's just A1, and it results in some probability distribution, and we have no samples of that probability distribution in passive learning. So in active learning, we now have the ability to choose what actions for the agent to try. And that gives us the opportunity to try actions that aren't in our policy. So this gets to active learning. And active reinforcement learning is all about the question of exploration versus exploitation. And exploitation is just this marketing word for using the best policy we have right now. And then exploration is the opposite. Is not using the best policy we have right now. And the naive approach to exploration is just to choose actions randomly. And that actually works fairly well in many situations, but there's other situations where that can just be a really bad idea. If you choose actions randomly, you're pretty much guaranteed eventually to explore every single possible transition and therefore get good data for all the transitions and eventually estimate everything perfectly. But it works a little bit better if you also shrink the probability of that random action over time. That is, most of the time you're going to take the optimal policy, so you get good rewards, or you get rewards that you've figured out are good from the learning so far. But then, as when you're in states or that you haven't visited often, that you haven't gotten much data on, you will very likely take a random action. But if you've already visited the state a lot of times, then you will want to take that random action not as often. And that's a general intuition we might want to try to implement. And one way to do it is this, what I've labeled on the screen as a better approach, which is that we are always going to act greedily. So we're always going to try to, using our current estimates of transition probabilities and utilities, pick the action that will give us the highest reward, highest future reward. But instead of estimating the true utility, we'll estimate a sort of over-optimistic utility estimate. And that's this U plus that's on the screen. And this is also from the textbook, so you can have a look there too. So the idea is that we have this U plus, and this U plus takes on values that look a little bit different than the usual Bellman updates, right? So instead of maximizing over the expected utility in the future, we estimate, or we choose a max value over this function f of all the best of the expected utility and some number. And so this n number represents the number of times we've tried out the transition A from state S. And so you can sort of get an idea that f is going to be this function that tells you how much should I trust my current estimate of my utility. And if I don't trust my current estimate of the utility because I haven't visited this state enough or I haven't tried this action enough times, then we're going to use an overestimate. We're going to assume that there's going to be some magical, amazing reward if we try this action. Okay, so here's an example of one of these functions, a very simple one that the textbook gives, which just says that if the count of the number of times we've tried this action in the state from this state is less than some threshold, capital N sub E, which is just some threshold, we just pick it. Maybe it's 10, maybe it's 100. The idea is just we just pick a reasonable number that says that we're going to do something. We're going to trust our estimate only once we've seen capital N examples of this state and action pair. Okay, and then otherwise, or rather, if it's under that threshold, if we haven't seen enough samples, we return R plus, which is some overestimate of reward. As the AI engineer, you would basically choose a reward that overestimates whatever possible rewards you would expect to get. And then otherwise, you would return the actual U value, the actual value of the sort of Bellman expected reward. So another variant of an active reinforcement learning algorithm is active TD learning. And sort of the weird thing about this is that the TD value update, or the TD learning update, is exactly the same as the non-active TD learning update. And it basically this happens because it doesn't really matter what action was taken. We sort of, the difference is that now, instead of computing the expected utility for a fixed policy, we're now assuming we're going to try to compute the original Bellman utility, which is the expected reward for the best policy. So that's annotated on the screen because I've dropped the pi notation. So the pi superscript is no longer in this equation, but the update basically just says, the same thing, is that we assume that the utility is an estimate of the reward plus the future reward, assuming we're going to play optimally. And we attempted to play optimally now, so now we know that this should be a good sample. This should, what we observe here should be a good sample of what the future reward is going to be. And if it's bigger than our current estimate, we're going to increase our current estimate. And if it's smaller than our current estimate, we'll decrease our current estimate. And in addition to just running these updates, which are really straightforward now, we also still need to keep estimates of the transition probabilities. So we sort of lose some of the benefits of TD learning in that, well, TD learning is, one of the magical things about it is that the equation updates, or the utility updates, all these equations don't include the transition probabilities at all, because all we're doing is we're sort of letting the environment give us these transition probabilities, but we never keep track of them. We never record them. We never even think about them in our updates. But if we want to have real policies in the end, we still need, or if we want to use these utilities to compute our policies, we need estimates of the transition probabilities. Okay, but we can get around that. And the way we do that is by computing something called an action utility function. And this is a function that combines the transition probabilities with the utilities. So rather than having a value for every single state, right? We had utilities for every single state, and then we had transition probabilities for actions within the states. Now we're just going to have a score that takes a Q function. This is a function, it's an action utility function. It's traditionally called a Q function. I'm still looking into why. I'm not really sure, so I apologize for you having to memorize what a Q function is and what Q-learning is. But it's a Q function of a state and an action. So now it takes in a state and an action, not just a state, but both things, and it returns a score. And the Bellman equation for Q functions, for action utility functions, is on the screen now, and you can see it looks very similar to the Bellman equation for utilities. But the difference is now essentially that the action decision is now sort of pushed into the expectation. And another way of defining Q functions is that the utility of state S is defined as the maximum over all possible actions of the Q functions for state S, right? Q functions for the actions from state S. And the intuition here is that, rather than having, just the utility of a state, which is the expected reward given optimal play from this point on, the Q function models what your future rewards will be given that you take some action A from state S. And it's a little bit like unrolling a level of recursion. And what that gets us is that we can write a very similar TD update to what we've seen so far. So this is the TD learning update for Q-learning, and it looks pretty much the same, right? It's again, you add or subtract some amount based on whether an estimate is close to or whether a sample is close to your current estimate. And just for convenience, let's look at, this is the previous, or the utility TD learning update for comparison, and it's kind of the same thing, right? So, the R of S plus, gamma times max over A prime of Q, blah, 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 that thing is the sample of what you observe. That's going to be what happens when we make the transition from S to S prime. And then we compare that to our current estimate of Q of S of A, and if that's too big, we increase Q of S of A, Q of S and A, and if it's too small, we decrease. So it's pretty much the same concept, right? It's just, again, sort of making these updates each transition we see, and then further, if we think about, now that we have these Q functions, we no longer need to even think about the transition probabilities at all, right? Originally, we would always have to think about them when we go to compute our policy. Maybe sometimes we don't need to think about them when we compute the utility, but when we go to compute the policy, we have to think about what the expected value of the utility is going to be given the transition probabilities. But with a Q function, all we care about is maximizing the Q function. So we just have to look at the Q function for the current state and choose the action A that maximizes that Q function. So for that reason, Q functions, or Q-learning, is known as model-free reinforcement learning, right? There's no model of the world, or rather, it's it's sort of hidden away in the Q function. And then finally, the last point I wanted to make in this video is that all this translates directly to the concept of an approximate utility function that I drew on the board in class. So you can do the same thing with Q-learning. You just need to define feature functions for some representation for the current state and some action. So up top you have here's a version of of an approximate Q-learning Q function, which is a linear function where we have these coefficients theta, and you have the features f. And the update equation for TD learning with Q-learning is the second line, and that's the general form. That's the general form for arbitrary G functions. And so in that general form, you have this partial derivative, which goes slightly beyond the prerequisites for this course, but most of you should be familiar with this, or at least maybe can remember it from, let's say, high school when you studied calculus. But for the purposes of simplifying, if we think about just the linear form of G, so like I wrote up on the first line, if the G function is just a linear function, then this gradient, or this derivative rather, is this partial derivative is just the function value. So this is the update, and this is the update you're going to use in your homework for computing an approximate Q-learning agent that's going to be able to play Pac-Man, even though the Pac-Man state space is really large. So let's just summarize. So what we covered in this video are general concepts surrounding active reinforcement learning. And I talked about active adaptive dynamic programming, where we choose random actions, or we act greedy and we overestimate the utility. Both these are reasonable things to try, and they both work fairly well and have some guarantees. Then we talked about active TD learning, which turns out to be exactly the same as standard TD learning, which is kind of a mind bender, but it comes from the fact that in TD learning, you don't really care, what action you took. You just sort of assume that the action came from the optimal policy or the current policy if you're doing fixed policy TD learning, and all you assume is that the transition that you observe is a representative sample of the future rewards. Okay, and then we talked about Q-learning, which is where we learn an action reward function directly, rather than thinking about the utilities and the transition probabilities as separate things. We treat it all as one function, and then we can use TD learning to directly learn this without having to think about the transition probabilities. And lastly, I finished up with just the idea that you can use an approximation And the approximation or the update for TD learning using the approximation uses the derivative of the utility function, and that's very easy if it's a linear function, because then you just take the feature value along that dimension, and that's the derivative. Okay, so let's talk about this stuff in class. There's a lot to go through and a lot to digest. So see you in class.